Good evening, everyone. So I'm working in Bloomberg, and Bloomberg has a lot of the JavaScript. The topic is OCaml is a. So before I start my talk, how many of you have written in static ML-like language before? Raise your hand. Okay, good. So it's the right audience. So OCaml itself is a very elegant language. It's small, compile time fast, run also fast. But JavaScript, you can tell JavaScript has a very, very huge ecosystem. And so we want to leverage the existing JavaScript ecosystem and also use our favorite programming language, OCaml. So create this project called Bucklescript, which is compile OCaml into JavaScript. And more than that, you can also use the JavaScript ecosystem. So why OCaml? So since you already use some static ML language, you already know, I assume you already know the benefit of the ML-like language. If you don't, there's a link, in the real world OCaml, see why all the benefit of the OCaml. And why JavaScript? Because the JavaScript is probably already the #1 most popular programming language in the world. The program number, and also it's everywhere. It's the only cross-platform language we have. Even Java doesn't have as many platforms as the JavaScript. And the Java, you have to download the JVM to run the code. And JavaScript basically gives you a link. You can show your code. And also, JavaScript is not only taking over the browser, actually it's also moving to the desktop. Like the GitHub released the open source project called Electron, and Microsoft built the Visual Studio Code, which is really good code editor on top of the Electron, the web technology. And it's the Microsoft also invests a lot in JavaScript. You can build native Windows application in I think in the Windows 8, since Windows 8, and also they are invested in the IoT, so you can write the JavaScript on the embedded system running the Windows 10. And JavaScript has a very large ecosystem. It has the npm package manager surpassed the Java package manager. 2 years ago, it became the largest package manager. So it means you have the huge amount of the libraries. And that's why we want to make OCaml integrate with the JavaScript even better. So the benefit of the Bucklescript is you write OCaml, but you run on the JavaScript platform. So the benefit it brings the benefit for both OCaml developer and the JavaScript developer. The benefit for the JavaScript developer, of course, is the OCaml has a very sound type system. So as long as you compile type check, you will not get any type error. And also have very higher both compile time and runtime performance. What means one major goal of Bucklescript is compile very, very fast, and also is generate code running very, very fast. I'll give you one example of we have a playground which compile the compiler into JavaScript, because the code, and you can see even the compiler running on the JavaScript backend is still pretty fast. And we have native backend which generate the assembly code. The same compiler just running in JavaScript backend and running in OCaml in native backend. You can feel how fast it is. For here, I change the code. Say this is first I remove the unused code and say I change the code. Hello OCaml, I add O, and you see it compiles and it runs instantly, even in the JavaScript backend. And it'll be even much faster in the native backend, because of course the assembly code is running faster than the JavaScript VM, even though we did a lot of optimizations. So for the JavaScript developers, now every day the JavaScript developers also use the transpiler called Bubble or TypeScript. So for JavaScript developers, they also have to build the projects. Bucklescript is much, much faster than Bubble or TypeScript, I mean, about the compile time performance. And for the runtime performance, we also, Bucklescript itself is an optimizing compiler. So it's not just transferring your OCaml code to the JavaScript code. It also does a lot of optimizations itself. And it also not only for the performance. Yeah.
I want to make sure everybody got it. So on the previous screen, you were showing that you compiled the OCaml compiler itself.
Oh, the thing is, it's because the Bucklescript is a compile OCaml to JavaScript, and it itself is written in OCaml, and there's already a bytecode compiler, JS OCaml, which compile the OCaml into JavaScript. We use the JS OCaml to compile the compiler into JavaScript. I think in the future we will bootstrap the whole compiler just in Bucklescript. Yeah.
Okay. So the results you were showing, that was the OCaml compiler compiled with JS of OCaml, not.
Right now it's in the JS OCaml, but in the future we want to bootstrap the whole compiler in Bucklescript itself.
Okay.
Yeah, and not only just performance, we also do the data elimination. It's more than the traditional way of like the tree shaking. So I think the ES6 module, they introduced like a static module system. So you can do some sort of the data code elimination. We do even more than that. We also do we shake the code in different level. In the function level, we found unused code. And if it's a pure code, we also remove it. We also do the purity analysis. And in the module level, we also, by the interface, we also do the data code elimination. And in the link level, we use the Google Closure compiler to do the further link time code elimination, data code elimination. So actually, it generates even smaller code than your handwritten JavaScript. And our today's topic is the benefit for the OCaml developer. So for OCaml developer, because OCaml itself, I mean, it's a very good language, but it has very, very small community compared with JavaScript. So we want to bring a lot of the existing JavaScript developer tools to the OCaml community. So this is a slide of what the Bucklescript like. So the top is the OCaml code. You define empty map, and then you add the key value pair 1 million times into the map. And then you try to verify if the key is in the map. I mean, the second for loop. And the below is the generate JavaScript code. You can see it's very, very close, right? I mean, even like we also generate the comments, like the empty map. I mean, for the OCaml in the runtime in JavaScript is 0. We also generate the comment, it's empty. And yeah, so this is, I mean, you can try in the browser too. So, I mean, this is the other example is the immutable, which is the Facebook immutable library, doing the same thing. It's also immutable map. You define a map, you create an empty map, then you add key value pair 1 million times, and then you verify if the key is in the map. So you can, from the table, you can see our code actually is 3 times faster than the immutable JavaScript library, which is written by the Facebook, JavaScript expert. This is not low bar because, I mean, they develop the performance tuning for this actually immutable.js is quite popular JavaScript library on the NPM. And also not only for the runtime performance, also for the code size. Because we do the data elimination, and we get very, very minimal, just 1 kilobytes. And the Facebook, I mean, you cannot do aggressive the data elimination for JavaScript because JavaScript is dynamic. For example, if I use a module, I can dynamic runtime query the method in the runtime, do the reflection. So I have no idea how to do the data elimination on the immutable.js, but so you have to if you use one JavaScript function, you have to pull in the whole library. For example, if I use one function from jQuery, I have to pull in the whole library from jQuery. All the payload I have to pay for the use of one small function. The funny thing is because of this, so they develop a lot of tiny libraries, like the L dash, the very popular JavaScript library called L dash. It has different sub-library, which is small, just for the avoid the payload. So in Bucklescript, you don't have to worry about this because the compiler will do this job for you and also do a very good job for you.
Can you, are you going to give us an overview of like the compilation phases? Like, I'm curious, when does the dead code elimination?
We do the dead code elimination in different levels. First, in the module level, we found the unused function because found unused function, and we found pure code, remove the pure code and unused function. And in the link level, we rely on the Google Closure compiler to remove unused function. I think one feature, also language feature matters because OCaml is a function language, or it's like a module, it's not a class. So it's easy, relatively easy for the compiler to find, unused code. Because if it's a class, if I only use one method, it's hard to say, oh, other method, you can just simply remove it.
So will that part maybe be a general purpose tool? Because there's a lot of other OCaml libraries, like for example, core, everybody complains it's too big. So could you just use this tool on core, even if you weren't compiling all the way down to JavaScript?
Currently, the Bucklescript work on the lambda code. So in theory, it should be this kind of the module level dead code elimination should be applied to the bytecode. Yeah, but it's a long story to also to upstream our change to the. But I think for the OCaml, the bytecode dead code elimination, we should do it more on the link level because even in a single module, if you expose 10 functions in the link level, you only use one function, you still want to remove the 10 functions, right? Yeah, so you see, from here you can see the generated code is very close. So the benefit of this is it has a very good interaction with the existing JavaScript and TypeScript code. So if you want to call the OCaml code Bucklescript from JavaScript, you don't need to do anything, just like TypeScript. I can show you here we have the functions, right? If I want to use the tail sum, here we just generate the tail sum. And name is guaranteed to be preserved. One OCaml module is mapped to one JavaScript module. So for JavaScript developer, if you want to use the OCaml library, you don't need to do anything. Just require your library, and then you have the tail sum function. You can just use it. So another good thing is you can distribute your OCaml code under the npm into the JavaScript library, and the user who uses the library doesn't even know your code is written in OCaml or whatever language. The cool thing is we can also let me show you. Leverage the existing JavaScript ecosystem. For example, in npm, there's a free service for the code hosting. So you can, because we upload the JavaScript, our library, OCaml library, which compiles JavaScript into the npm. Then the free service, you can try the library in the browser for free. Here you can say require base plot from the lib.js list, or just load the list library, right? In the standard library, OCaml library, say run the code. You see, you can load the list. This is a list module in the OCaml standard library. You say, yeah, list.append, assoc, all the OCaml functions you can get for free. But this is because of the awesome JavaScript ecosystem. We leverage the JavaScript tools. And we also have some experimental support for the TypeScript. Our compiler will spit out the TDS file, which is the TypeScript declaration files. So it can be consumed by the TypeScript compiler. So it means you can write OCaml and it will work with so if the TypeScript want to call the OCaml code, it will still work out of the box. And for the third way is you need to call JavaScript from Bucklescript, because JavaScript is a dynamic language. So just like TypeScript, you have to write the type declarations, and I will show you later. So for simple FFI, it's very simple. You just write the external. External is the OCaml way of defining the FFI. Here we define external array map and define its type. Give first argument is array, and second argument is a function, prime A to prime B. And because JavaScript is the calling convention of JavaScript is uncarried. You know, OCaml is a carried language like Haskell, OCaml, and F#. I mean, it's a carried language. Every function only accept one argument and return another function. But JavaScript is the calling convention of JavaScript is the uncarried. So here we have annotation like the attributes. Attribute uncarried. The second argument is a function. The return array, and then you can just call the function. Actually, I can call and then you can just call the function. And you see the generated code is pretty. Yeah, this is the basic simple FFI. Yeah, question.
The location of the uncurry annotation is curious. I don't get it.
So the uncurry, you can think of it this way. Prime A, arrow prime B has higher precedence. So the uncurry attribute is applied to the whole types. You can add a parenthesis, but it's not necessary. So the attribute, because the arrow has a higher precedence in OCaml, so prime A, arrow prime B, and then the whole is applied to uncarried attributes. Yeah, cool. Yeah. So for simple, if we
why don't you need another uncurry for?
Because you will need to produce an uncarried function in OCaml to be as a callback from JavaScript side. JavaScript accepts an uncarried function. So here in OCaml side, you have to produce an uncarried function to the JavaScript. Because the JavaScript is uncarried, the OCaml have to produce an uncarried function to JavaScript.
What was your question though?
I'm curious why there's two arguments to the array map function, right? Yeah. The array and the actual function which does the mapping, right?
Yeah, it's uncarried, yeah.
So why do you need the uncurry annotation on the second function to array map and not
You need both, not neither.
the second one for the actual function that is uncurried? Like why it seems like array map can itself be curried, right? Like I could say array map of an array, and then I'd have a variable array.
Oh, the thing, you mean the array map itself need to be uncarried? Yeah. Oh, the thing is the OCaml compiler. Oh yeah, the thing is because the external was originally designed for the CFFI. External, the keyword was originally designed for the CFFI. So C function accepts uncarried. C is the uncarried function. So the OCaml compiler already does this for you. So the external, I mean, because the OCaml compiler already, for the CFFI, it already does the uncarried for you. So it's not necessary anymore for the external. Yeah. Cool. So this is for the simple FFI, for the math, I mean, for the simple function. But for the complex scenario, you want to have objects. So here I give you an example. If we want to write a HTTP server using Node.js, and yeah, so let's go this way. I mean, so we want to write a binding to the Node.js, the core API, HTTP object. So we want to define the types for the HTTP object, especially for this function, create server, right? So here we define request. Here for this tiny example, we don't care about the request. We just always return some value. So we can define request as the abstract type. And we will write a response. So we can say response is an object, it's a JavaScript object. Here we have js.t. So the brackets is a OCaml object orientation, right? So js.t say, oh, this is a JavaScript object. Then you define the response has three methods. One is the set the status code. The other is the set header and the end. Because the thing is the end is a keyword in OCaml. So here we added a double underscore to distinguish from the keyword. You cannot write end column because it's a syntax error. And because OCaml doesn't have OCaml is an object language, but doesn't have the setter. So everything in OCaml is a method. So here we introduced the double underscore set, which is the setter for the object. And say we define the request and the response. Now we define the HTTP object type. It's also a JavaScript object, has a one method called create server. You take a callback. The callback function is the given request and the response. Return nothing. And then the create server itself return a server object. So here we define the server as a JavaScript object which has a type listen, which takes the a table of 3 values, the port number, the host name, and the callback. And in the end, we define HTTP, which is from the module. The Node.js HTTP module has the type of HTTP. So I guess people will have a lot of questions. If you have a question for the... Oh, OK.
Okay, first of all, it looks like, are you using PPX for a lot of those annotations? Is that correct?
Yeah, the onCarry is actually the same as the, if you go below, onCarry is the same as here, actually onCarry. But the thing is, you have to write a lot of onCarry. So which is like a little syntax sugar. The pattern onCarry means apply the onCarry to all the functions. So basically, it's a very simple rewrite rule. It's a PPX, but the rewrite rule is very, very simple. Just apply the attribute onCarry to all the functions.
Okay, just a minor detail with this example. Like, I noticed you made a tuple for the request and the response. Is there any particular reason for that? Is that like?
Because the JavaScript calling convention is onCarry. OnCarry means you have to give all the arguments at the same time, right? So you have to, for all the arguments, you have to make a table instead of the. So in OCaml, I say prime A, prime arrow, prime B, arrow, prime C. But in JavaScript, I say prime A, star, prime B, arrow, prime C. Because JavaScript is the one way to do this, JS OCaml do this is do the runtime dispatch. So you have to pay for the performance, and the JS OCaml relies on the one property called the function.prototype.length. Actually, this is not reliable because some JavaScript library do very, very crazy stuff. They will check your function.length. If length is 0, they will do something. If length is 1, you will do another stuff. So if you rely on length, you will get screwed sometimes. So here, we solve the problem. We don't rely on the function.product.length.
Thank you.
So here we define type, and now we can write the OCaml code. The top is the OCaml code. The below is the general JavaScript code. You can see we define the port number, which is 3000, and the host name is the local host name. And then we write a function called create server, giving me a HTTP object. Here, the double hash is the same convention of the JS OCaml, just like the object dot in JavaScript. So we say we use the HTTP dot create server and take a callback. The callback is of type request and response. And then we set the status code, which is the 200, and then we set the header, and then we finish the response with hello world. And then, because it returns a server object, we listen to the port number, server listen and port host name, and another callback, which is do the login. And below is generate the JavaScript code. This is real code. I will do the demo later. This is real generic code. You can see it's very, very close. And the cool thing is here, we don't write any types. We don't write any type declarations because the OCaml compiler does a very, very fancy job. So for even the HTTP, which has it's an object type, and it has the create server method, and the OCaml compiler, we do all the type inference for you. So this is very uncommon because this is a struct typing. So for Haskell do type inference for you, but Haskell doesn't have the struct typing, right? So so far as I know, only the OCaml language has the subtyping and struct typing native support. And then yeah.
Curious, why did you get rid of the port?
Because the compiler do the inline port. because port is compiled to the inline.
So why did they get rid of? Why did it decide to inline port but not hosting?
Inline is very, I mean, it's a magic basically. inline, the compiler inline is the magic. The reason here is the host name. The currently in OCaml, the underlying string is still mutable. I mean, it's immutable. It's a flag called the safe string, so we'll verify the string is immutable. But the underlying, the compiler implementation still doesn't take advantage of this, so you cannot like move the string away. But we will do this later. I mean, but basically the inliner is a magic. You can, yeah.
Can you declare host name as a constant, and then it would work?
So it's already by the OCaml let host name is already a constant. Just the compiler doesn't take advantage of this right now. But maybe next week we'll take advantage of this. Our Bucklescript is moving very fast. Maybe yeah.
I mean, it's one weird consequence, right? Is like, in OCaml you have that check string for the port, but later on you get, because you inline the port, you rely upon JavaScript to do the conversion from an int to a string.
Oh yeah, the thing we do the very smart thing. So we know the string of int is just like plus. Yeah, we do the smart thing here. So here
Is we thing to do? Like,
yeah, because the port in JavaScript we do coercion.
It would do it even without that.
yeah.
Because the JavaScript we do the implicit conversion. Actually, very fast. If we say any value plus a string plus any value, we coerce the value to a string.
But are the details all identical in these kinds of conversions? Like, I mean, you want to preserve semantics, like precise.
Yeah, this is documented. This is a standard behavior. So any string plus a value, you will coerce this value to a string. And because we know the port is an integer number, and this coercion is correct, so we take advantage of this.
So this is for string of int.
Yeah, string of int. Only
If you
for
were
string of
doing
int.
string of float or using like sprintf, it would not inline
Yeah.
and
Only
use the
because
JavaScript coercion. It would just do the actual. If you show later the printf, you'll see that it's using the actual OCaml printf.
Only for string of int, because the underlying string of int is yeah. Because the underlying of string of int is a safe function, and we know, I mean, it's the semantics, so we can do this in a safe way. And here, we define the create server function, and we have the FFI for the HTTP object. Now we just create a server in another file, like create server, give it the me object, and then below is the generated code. Now you have a whole HTTP server written in OCaml and running in the JavaScript platform. And it's exact code. I mean, there's no, for most like the language compiled JavaScript, it generates huge monolithic JavaScript code. Here we generate quite readable, I mean, JavaScript code. You can even deploy, like for this, for example, you can even deploy the create server as a function to the NPM as a package, and the JavaScript developer can use this.
Can you disable the inline if you want to?
Yeah, currently we don't have option to disable inline, but in the future it's on roadmap to disable some optimization to get, because the optimization is a little in conflict with the readability. I mean, if you do the too aggressive optimization, then to some extent you will lose some readability, but we will provide some option to disable for the dev mode. Yeah. So now I will explain a little bit the underlying. So why it's possible? I mean, because means why you can compile OCaml to very readable JavaScript, why without the sacrifice the readability and also the performance. The reason is OCaml is very like JavaScript if you ignore the types, because the JavaScript is a function language. Actually, JavaScript is the first major mainstream function language. It has first class function, it has the lexical scope, it has the closure, and OCaml, of course, is a function language. And JavaScript is also object-oriented language. It has objects, it has a prototype, it has inheritance. And OCaml, object-caml. Remember, the name of OCaml is object-caml. OCaml has a very good support for the OO style programming. OCaml has the struct typing, row polymorphism, and inheritance. Even have multiple inheritance for OCaml language. Yeah, so actually the object part of OCaml is not very well known, but actually it's very, very powerful. The OCaml object language is the type inference for the object. Before TypeScript become popular, not too many language has a struct typing, but TypeScript doesn't have the type inference. You have to write the interface for TypeScript code. TypeScript also has struct typing, but you have to write the type declarations. You don't get the type inference for free. But OCaml do even more. And the only lacking bits of the JavaScript is it doesn't have type system. OCaml provides this. So if you think of this way, when we compile OCaml to JavaScript, we just erase the type, do the type erasure, then you get the JavaScript code. And the good thing is OCaml also has a very similar module system to JavaScript. The OCaml doesn't have namespace, unlike Java. So, and JavaScript doesn't have namespace. So basically, and with the forthcoming, the ES6, JavaScript has the module system. Basically, one file is one module. And OCaml has shared a similar feature with one file, one module. So basically, you can map one OCaml file to one JavaScript module. And that's actually the OCaml, it's used a lot in the foundation work of JavaScript. For example, the ECMAScript 4, they deprecated the JavaScript standard. The reference implementation is written in OCaml or ML or SML, I'm not sure. And also like the React.js originally was written in React ML, in the standard ML by the Facebook. React.js is a very popular front-end web framework, like the AngularJS. Two of them are the major front-end web framework, React.js and AngularJS. And also, now the forthcoming the new standard of the WebAssembly, the reference implementation is also written in OCaml. Actually, I can show you the website. You can see the specification was written in OCaml. Yeah. Okay, so now we go to a little internal of the Bucklescript. It's optimizing JavaScript compiler, generate the optimized JavaScript code. It's leverage. It's not all my work. We leverage existing OCaml compiler toolchain. So we have two modes. One is dev mode. Dev mode, we don't do any name mangling. Actually, we do our best to restore the names. For example, like if it's the same variable, but if it appears in different scope, and the scope there's no overlap, we preserve the names instead of generating some ugly names. And it's very, very fast. Compile time very fast, and it supports separate compilation. So unlike most transpiler, like the Scala.js or like the Clojure script, they compile for example, Scala.js compile the one Scala file to one IR, and they have a linker, the link the IR into a huge, monolithic JavaScript code. We generate for one module, we generate one module JavaScript code, and then you can use the existing JavaScript bundler like Webpack or Google Clojure compiler to do the bundling. So because there's no global compile, so you have very fast feedback loop. If you take Scala.js, for example, you have to compile each file into IR, and then you have linker to link the IR to the JavaScript, and then you can run the code. It takes a lot of time for the compile.
If you're leveraging the standard OCaml compiler, why do you need the PPX stuff? Like, why not just automatically say, if I have a function declaration, I'm not going to have it. I'm going to have it in its uncorrect form.
The thing is, OCaml is you can just compile every OCaml function to carry the form, like given one argument. Only so if you like compile all the OCaml function in the uncarried form. Meaning every OCaml function, prime A, arrow prime B, arrow prime C, will be like taking one argument, return another function, and taking one argument, return another function, right? This will be super slow. Because OCaml, the VM, optimize the carried calling convention, and JavaScript VM doesn't optimize the carried calling convention.
I think his question is different.
Yeah, I understand that. I'm just saying, if you're already leveraging the OCaml parser, why do you need those PBX annotations? Why not just automatically assume that every time I write a fun or that binding with multiple arguments and what have you, that I want the uncurried form of that function?
So the thing
automatically map it into the star form, right?
The thing we support both the carry and uncarried calling convention. So in OCaml language itself, we still support the carry by default. Every OCaml function is carried, and we do the optimizing here. Because the code is written in OCaml, we saw the source code. We will remember the arity of the function. So we see all the arguments. We will take advantage of the information to avoid the cost of the carried cost. So we support the carried calling convention and uncarried calling convention. We support both. So I'll give you one example, like PureScript. PureScript compile all the functions into carried form. So basically you have to pay for a lot. For every function, they'll pay for the allocation of the closure. So here we take advantage of both. If you deal with JavaScript, you have uncarried. You don't pay for the performance. And you deal with OCaml, you can still use a carried feature. And because the compiler optimizer will try to remove the cost of the carried. So it doesn't change the semantic of the language. It's still carried by default. But you can use the uncarried for the performance and for the FFI.
So can you assume that all external functions will be uncarried?
Yeah. All the original OCaml compiler already guarantee this.
So in that case, why do you have to add it?
It's a callback. So in our example, here there are two functions here. Array map is an outer function. It's guaranteed to be uncarried. But the internal callback, it's another function, right? This is not guaranteed. We have to make sure it's uncarried.
So while we're on the slide, what is the, I'm assuming that's another annotation, the colon?
Test and uncarried? Which one?
The second line.
Second line,
Last annotation.
Which annotation?
At BS.
BS.call.
Oh, it means this is a JavaScript call function. So actually it's very cool. So you can have we annotate this JavaScript calling function. Because otherwise it's a C function. It's a C function. So actually if you have one external, you can define a C function and a JavaScript function. And then depending on the backend, it will pick up different libraries into the linking. So you can write the one FFI for both C language and JavaScript. Question? So we have, dev mode, we do and in the production mode, we use the Google Closure compiler to do the link time optimization, and also remove the unused code further. So the result is you have faster code, and also smaller code, and because OCaml is type-safe language, you have more robust code. So we address that. I think one is because people use the dynamic language because there are some good things of the dynamic language. You don't need to compile, just refresh the browser, and you can see your output. And because we try to make the compile time as fast as we can, actually it's even much faster than Bubble itself. So I think we try to make the developer experience even better. And the workflow is we use most of the OCaml compiler toolchain. If you take a look at this graph, is the high-level description of the OCaml compiler. So first stage is given me a source code. We do parse and pre-processing. You get a parse tree, which is basically the surface syntax. We use the existing OCaml parsing, and we do a little rewriting using PBX on this level. And the type inference and type checking is also already implemented by the existing OCaml compiler. And then give a type tree the compiler will try to compile away the pattern mesh. And we also make use of the existing pattern mesh compiler. Now we have a number expression. The number expression has almost all the skeleton of the OCaml code, but the number expression doesn't have any type information. Our work is taking all the number code and compile to the JavaScript code. At the same time, we also generate the CMJ file, which contains the metadata of the code for the cross-module inlining and cross-module optimization. And the other two backends is the bytecode. You can also compile the lambda to bytecode. And you have an OCaml VM, OCaml run, the run code. And then you can also compile OCaml lambda to the C minus minus, and then you go to the assembly code. So basically, it's another backend for the OCaml language, but the front end and the middle end is reused.
So I don't know enough yet about the Lambda part of the compiler. How dependent is that on evolving OCaml language features? So since OCaml seems to be evolving quite a lot now on, will you be able to keep up with changes, or is Lambda pretty stable?
The change of Lambda? So the thing is, Lambda, I think, is quite stable. The major changing part, I think the path tree and tab tree is moving every release. Number expression is like, basically if you want to add a new primitive, for example, if you want to add a new location like the underscore log, right? The new feature, then you add a new primitive. The skeleton of the Lambda code doesn't change too much. If you want, the change is most like add a new primitive function, C function, I mean native, like the, like you want to add some new primitives. It changes, but the skeleton is the same.
So a related question, how much of the OCaml language have you covered? Is it all of it now?
Yeah, all of it.
All OCaml
all
code
of it
can...
except the garbage collector runtime. So the garbage collector GC module doesn't make sense. And OCaml has a wiki map, which is not supported in the wiki reference. It's not done support in the JavaScript. And the I/O stuff, the language-wise, they're all supported.
But some libraries are not.
Yeah, like the Marshall. I mean, these are very tied to the runtime, the C runtime behavior. Like the Marshall, like the hash table. The hash table algorithm is the same, but because the OCaml hash table has a 31-bit limitation, we use the same hash algorithm, but we don't have this limitation. We can do even better in this case. I think all languages support it except some. Oh, and another exception is the object module. Object module, because the object of magic. I mean, you can do anything with. Yeah, this is so basically the number behavior is a little different because in OCaml you have the 31 bits. In JavaScript we provide the 32 bits. We only have 32 bits and 64 bits. And yeah, I think that's almost the same. Yeah, almost the same. And I think all because we reuse all the front end and the middle end and tab checking. So the original OCaml compiler already did a lot of work for us. So the int, actually OCaml int is a platform dependent. In 64 platform is 33 bits. In 32 platform is 31 bits. We all compile into 32 bits. Yeah, so we do a little comparison with other way. I think the most famous one is TypeScript. TypeScript get a very readable output code. I would say, to be honest, I think the TypeScript generates even more readable output code compared with Bucklescript. But we are very close, and TypeScript has a great editor. But I think the major thing with the TypeScript is it compiles very slow. Because TypeScript, I mean, it's compiled, has only one backend, JavaScript. You can only run TypeScript compiler in the node. I mean, and you have to start a VM and we have to do a macro benchmark, which have two files. One is OCaml function, OCaml file, which has 500 same Phoebe functions. The other is TypeScript function, which has another 500 Phoebe functions. And you can see Bucklescript is almost 20 times faster than TypeScript compile time. Actually, TypeScript compiler is not the slowest transpiler. It takes Scala. I mean, it's even slower. You can see the compile time is very good. It's very good. And TypeScript doesn't have a TypeScript has a type system, but it's unsound. So basically, you can have better tooling with TypeScript, but you don't get any guarantee from the TypeScript language. I mean, you can still even have like TypeScript nice TypeScript code, it will still have type error in the runtime. And the other thing is TypeScript does very little type inference. So basically, you have to write a type annotation everywhere. It's like very like C#. You have to write a type annotation for the argument. And the other thing is TypeScript doesn't only have JavaScript backend. So if you want to run the down to the metal, I mean, the only option of you is JavaScript. You can only run your code in JavaScript backend. And TypeScript try to make the output as readable as he can. So basically, TypeScript doesn't do any code optimization. Even the simple like tail call optimization is not done in the TypeScript compiler. I will show you like for example, in our stuff, you can see I just removed the code. You can see tail sum is a tail call function. We do the tail call optimization of the aux function to a while loop and an inline function. Here tail sum, right? But just TypeScript doesn't do any optimization. I mean, TypeScript doesn't do anything. Yeah, and OCaml has a lot of backends. OCaml can be compiled to ARM, can be compiled to Android and iOS. And the cool thing, we even have the unikernel Mirage, which means in the future you can run your code in a very small language customized VM. The other similar work is by the JS OCaml. I would say Bucklescript actually is the Bucklescript was inspired from the JS OCaml. I mean, JS OCaml is a very good compile OCaml code to JavaScript code. Basically, you get the bytecode and then you run JS OCaml, you get the JavaScript code. I think the major difference is the readability and the FFI. In JS OCaml, basically you have give a bytecode, generate a monolithic JavaScript code, and then run your code. You don't need to care about the JavaScript. But here we want to make the OCaml has a better interaction with the existing JavaScript code. Difference is if you are into the internal of JS OCaml, you will see first for the simple FFI. For the simple FFI, for like the array map, for this simple, there's basically no PPX. The attribute is like it's not PPX. It just this attribute will be passed down to the Lambda code. So there's no PPX. Just write the attributes. And for JS OCaml, if you know the internal of JS OCaml, it has very, very complex rewrite rules for how to do the PPX. And the other thing is the JS OCaml doesn't have the native support for the on-carry support. Basically, you have the call function you want to call in the wrap method callback, and the JS OCaml will rely on the function.prototype.length to runtime dispatching. Yeah, and for the object part, I think our rewrite rules is still much simpler. If you run the dsource to see the source code, basically the double hash, the local rewrite rules will be fn.run arity, and then the method name, and then the arguments. So the rewrite rules is local, and we don't generate a bunch of the. So how JS OCaml works? JS OCaml will try to use the PPX to interact with the existing type system to get the type inference correct. We don't need this. The thing is we have the method name. For example, like double hash. In the Lambda, we already know the method name. But in JS OCaml, they have to use the very complex PPX to get the type system correct and also pass the method name into the bytecode. And of course, there's very good advantage of the JS OCaml. It's very non-intrusive. Means you don't need to care about anything. You get the bytecode, and then you run JS OCaml with the bytecode, you get the JavaScript code, right? Basically, you don't need to do any extra work to get your OCaml code running on the JavaScript platform. In Bucklescript, you have to build using Bucklescript. I mean, it's more invasive than just OCaml. So, yeah, so the future work is we need to do more battle testing. And also we want to write the bindings to the existing JavaScript library. We want to use the TypeScript compiler API to take the existing TypeScript declaration files and generate the FFI code for the Bucklescript. And also, currently the compiler is only targeted against the 4.20.3. The latest one, I think last week we made a new release, which is the 4.23. We also need to catch up the latest compiler. And of course, always more optimization. So, yeah.
This code you gets this, but one of your key points is a reasonable, sorry, I'm just not doing that. A reasonable format. Can you show an example of what like a complicated pattern match would look like? How does that get like rewritten in JavaScript? And I was thinking about that. And what does a functor look like?
Functor, I can show you. It depends. I mean, it all depends. So, for example, like the So here you see it depends on, here we inline the functor. So you will see and you can see the code. But it all depends, I mean, case by case. But you can have a look at the generic code.
You annotate the type of X on purpose, or
What?
in the definition of compare?
Oh yeah, because polymorphic compare is evil in OCaml.
Right,
You never want to use a polymorphic compare.
But
Right.
does the compiler pick that up then when you put the int?
If you use yeah, of course you can use the non-polymorphic compare. Then we do the camel object compare, which will be our runtime support. The cool thing with Bucklescript, if you know JS OCaml, you know the runtime is written in JavaScript. But in Bucklescript, the whole runtime is written in OCaml itself. Because the reason is in Bucklescript, it's very easy to consume OCaml library as JavaScript code. I mean, if you do this in JS OCaml, you have to manually write what function you want to export and make sure it's correct. Here in Bucklescript, the runtime is written in OCaml, and you can just consume the runtime as a JavaScript library in the compiler itself. And if you know the reason, the Facebook made a new release of a reason, which is a new interface with OCaml. We also support this. I'll give you a playground. So the left side is the new syntax for OCaml, is a reason, and then the right side is generate the JavaScript code. And because the reason try to make the syntax more like JavaScript, so if you see it's even more, the input code and the output is even more close. How much time do I have? So yeah, go.
7:35, so if there's more questions, keep asking. If you want to use the mic, great, but I won't force you.
I don't know much about JavaScript, but I just was curious, like, when you have to code variants, is there any consideration when they get converted to JavaScript? Because JavaScript doesn't have native variants necessarily, right?
Yeah, JavaScript doesn't have a variant. So the thing we encode the variant as an array. If you like actually I can show you something. So it's still case by case. For example, like for the option, Because we have a playground, I should just show you the. Let's go back to the OCaml demo. Depends on the variant. So for simple variant, like here the list. You see the list? For this one, you see the, let me. This map, you can see that we have a const, right? Map function. Const, you see when we create a const, it's just an array of 2 elements. Const have 2 elements, right? And here we have the const is an array which has 2 elements, the first element and the rest elements. For this simple variance, it's basically an array and with a tag. Here the list tag is not required because you have only 2 branches. And one is a constant, the other is, you can tell the difference. The OCaml runtime is already good enough to tell the difference. So here the tag is not necessary. For other more complex variants, you have an array and with a tag attribute. But it's unlike the JS OCaml. JS OCaml has, for example, JS OCaml, if you compile an array to JavaScript array, the first bit, the first element is 0, is reserved for tag. But here in Bucklescript, our OCaml array is JavaScript array, exactly same array. And because and the OCaml variant as a JavaScript array with the attribute tag, it's not in JS OCaml. It reserves the first element as a tag.
Okay, and actually, it kind of follows up to my next question, which is, why would I pick Bucklescript over just using JS OCaml directly? Like, when's a good use case for one versus the other?
I mean, yeah, I mean there are different use cases. If you run your OCaml program exclusively, you don't want to interact with the existing JavaScript system. And I mean, perfect JS OCaml is really good. I mean, you can just keep using it. I mean, if you want to take advantage of the existing JavaScript ecosystem, you want to write your OCaml code and deploy the npm package to get more people use it, then you can try the Bucklescript. I'll give you another example how we reuse the JavaScript ecosystem, like the coverage. Because our code, the runtime and standard library is compiled to JavaScript, you can just reuse the existing JavaScript coverage. So you can have the coverage test. You can see the, say I pick one example. All the coverage, I mean, code is guilty. I mean, you can take advantage of existing JavaScript tools. And for another example, you want to deploy code into AWS Lambda. And because I believe our way to the FFI is easier than JS OCaml. I mean, it saves you some work. If you don't care about the JavaScript ecosystem, I think JS OCaml is your better bet. Yeah.
Okay, thank you.
I think if you can utilize TypeScript.
Yeah, we have experimental support. We also generate the .d.ts file. So TypeScript can just call the OCaml JavaScript. Yeah.
It's like the other way that's really interesting because then you can use, you don't have to write your own bindings, you can just pick up the TypeScript communities.
Yeah, so actually, as I said, the future work, one of the future is to use the TypeScript compiler to give a .d.ts file and generate the FFI for the Bucklescript. Yeah. So.
Question. Is the mic on? Yep. So the Clojure language, which is a Lisp, has a JavaScript backend. They call it Bucklescript. Yeah. And one of the really powerful things you could do with it is you can actually connect to a running browser, and you can eval some.
Figwheel, right? Figwheel.
Yes. Well, Figwheel is a tool that works around that, so you're familiar with this. And essentially, what you can do, just for everybody else, is that you can incrementally update your program without having to even reload the page. So you can, change the definition of callback functions and such without even, you can keep all of your browser state, which is really powerful. Is there an equivalent with
yeah, basically, because I think we do a separate compilation, so there's no reason we cannot accomplish this.
So is the output a bunch of JavaScript files?
It's like one OCaml file, one JavaScript file. I think, give me 5 minutes, I just do a very short demo. So here's one file, one is the example, the HTTP server written in OCaml. And I run the code, so if you see the directory, I remove the general JavaScript code, right? Now I run a compile, use the BSC, -c, the ML file. Now I run the code and generate JavaScript code. It's very fast, you see. Now I have the JavaScript code. I can run the server on the fly. Here you can see this is ML, this is JavaScript code, and this is the OCaml code. And now I make a typo. Here I make say, okay, let me typo say not compatible. There's no method. Status code. You see. Now you have JavaScript code. But actually, JavaScript is even shorter because there's no types. Right. Left side is OCaml, right side is JavaScript. The cool thing with the OCaml is in TypeScript, you have to separate the type declarations and the TypeScript file. But in OCaml, the types is inherent in the language part. So you can just deploy your OCaml types, the binding as normal OCaml libraries onto the NPM. Then people just consume as you don't need to have like TSD. In TypeScript community, there's like a TypeScript package manager, just manage the type declaration files. Here we can just use the same language as both as types and the implementation. Don't need to make a separation.
I guess another point, more generally, how do you walk the line between creating immutable data structures and immutable ones? Like what is a reference end up looking like? Do you just compile a reference down to a normal JavaScript variable because you can mutate it?
What do you mean?
Like, suppose you have like a let x equals 3 into the system let binding, and then later on you redefine let x equals 5, right? Within the scope, like value of x is changed. Do you compile that to a JavaScript where first you assign x equals 3, and later on you write it with 5? And then how would that contrast with like x was now a reference where you had to change?
The type system will prevent you doing this. In OCaml, if I let x equals 3, you cannot mutate anymore. You have to
you can define let x equals something else later on, right? Within the same.
Yeah, I can show you. So I can just let me erase this code. So here you want to say let x equals 3 and let what you want. So you can compile. And because we do very smart thing, because the last x shadow the previous x, and the previous x is not used. We only export 1. But we want to, because the compile is it's a little too smart. Actually, I cannot show you an example because both x but I can make a side effect. I show you. Yeah, it's still too smart. So here is the the basic idea is you have let x equal 3 and let x equal 4, and the first x will be still x, and the second x, if it's not erased here, will be x$1, something like that. But here, because x equals 3, it's not used and it's pure, and we just remove it.
And so what would happen if like x was a reference?
Reference is depends. So if the reference is not escaped, if the reference is not in a for loop, it's not escaped, we will just compare to a JavaScript variable. If the reference is escaped into a function, it will be a singleton array. Array has only one element. Question?
One more question. So what's the largest program you've built so far with this?
What mean large? So it's still in not production ready. But we have a lot of tests. For example, we have one. We have we have a product buffer compiler which compiles JavaScript and just works. Yeah, it's not here. I think like 6,000 line code compiles JavaScript and just works. Yeah. We have like around 1,400 tests. I think we need to do more tests before production release. Yeah.
Have you tried compiling the entire library? Like something?
Yeah, like the runtime. Oh yeah, also the runtime. I think like several thousand line code written in OCaml is all compiled to JavaScript. Runtime and yeah, we eventually want to bootstrap the whole compiler.
Just run it on core real quick. I'd love to see the result.
The core has a lot of the, C stuff.
Core, no.
Yeah, we'll give it a try. Yeah.
Quick question. On slide 14, you had mentioned implementation of F lambda as a future performance increase. I was wondering if you could go into a little detail about that. Or
Which one?
Yeah.
This one?
Yep. To faster in the future with F lambda.
Yeah, because
enabled.
the thing that our compiler is only take the lambda expression and compile JavaScript, right? F lambda is optimizing backend for the OCaml because our compiler is written in OCaml. So if F lambda do the work, say for the same amount of work, our compiler will definitely get faster. Because F lambda can make native compiler slower because you have to take time to optimizing. But for our Bucklescript compiler, it's the same amount of work. We take a lambda and compile JavaScript. We don't go through the F lambda, but we can enjoy the F lambda the optimization.
Okay, thank you.
We'll get beer now? Go drink. Well, thanks a lot for the talk. That was really awesome.
Thank you.